All right. Let's see. Happy Thursday. How's everyone doing? What's that? Yes, top hat. Yep. What's this, our second day? Isn't it our second one? All right. Y'all ready for a medium-sized set of topics today? I think medium's good. Yeah, I agree. So what we're doing today is closing out part 4. We're talking about our last main kind of relationship between two variables, which is time series. Let's see. Tuesday next week we're going to talk about. So in class we'll do a bit of a review for the mini exam on Thursday next week, and then we'll also talk about part 4 projects and final projects. So just putting these things back on our radar, thinking about like how to put our projects together for the end of the semester. We're kind of in the last stretch here. We're almost done with part 4. All that's left of like major new material is part 5 after today. And then part 6, we're gonna spend a few days just talking about projects and how to communicate with data. So that's where we're going. Let's see. There are 2 homeworks that are live at the moment. So homework 4.1 and 4.2. I've scaled some of these back. So I'm only asking some questions that I typically do. But I'm giving them all to you just so you can see some of the questions I've asked in past semesters. Let's see. And then after class on Tuesday, I'll check in with you all and see if we want to hold an extra review session. I'm hoping that what we do in class partly covers what we would typically do in a review session. And I've also posted the demo, which is from last semester, but it's going to be almost everything identical this semester. Let's see, anything I'm missing? Any questions? Do you want to be outside? I spent all morning thinking about ways of taking this class outside, and I don't know how possible that would be. I guess if we all took our computers, you have my slides, so you could possibly look at the slides and we could just sit in the grass, but unfortunately my voice is not loud enough to carry over traffic sounds, so. Okay, what if we keep class quick? Should we do this in under an hour and 15 minutes? Why are we still talking about this class when it's so nice outside? I hear you, I see you, I agree. I'm doing my job and so are you, so that's great. Everyone got their code? Yeah. All right, so what we're doing today, we're talking about time series. I'm calling this the problem of time series. A lot of you will be tempted to work on time series models for your final project. Every semester, I have some students do this, and it's not wrong to do it. I'm just gonna show you the reasons to avoid it in general. This is not a time series class. I've had students in this class before simultaneously be taking a time series class, which is the whole class is devoted to thinking about time series models. It's that tricky of a problem. What I'm doing today is showing you where the problem arises, some of the simplest techniques for approaching time series models, and then I've used this as a caution to be very careful if you end up working with it. If you do end up working with a time series model, just document the limitations. That's the way to handle it. You don't have to be perfect, you just have to be correct. And those are different things, right? show me the limitations of your model if you have them. Okay, so look at that. The slides are not posted. The exercise is posted. Let me fix the slides after class. You can't access my file system, but I have the slides, which we're going to work with. And I'll post the slides after class. So this is called the problem of time series. The main goal is exactly as I've just mentioned. Like, I just want to communicate to you that there are lots of pitfalls when you're working with time series models. Last class, we talked about the 4 main assumptions of the general linear model, which is linearity. So we're going to assume a linear relationship between our 2 variables. Homoscedasticity, so this is like equal variance across every part of the x value. So the predictor variable, we just need the variance to be consistent across all x. Independence, so this is observations are independent from each other, which is the one we're going to focus on today. And then the last one is that errors are normally distributed, which is the one we can sort of not worry so much about if our sample is large enough. The central limit theorem means that we don't actually have to have normal error terms if our sample size is large enough. So what we're doing today is focusing on assumption 3, which is independence. Sometimes you'll see, a data set that looks like this. We have one value, so one measure that's repeated through time. I think this is more often used in macroeconomics. So our exercise today is actually going to verify a macroeconomics concept. How many of you know ECON's law? Okay, maybe only one person. ECON's law is a relationship between a transformed GDP value and unemployment. So it tells us something about how unemployment and GDP move together. I'm not a macroeconomist, and so this is like a little outside my core focus, but I think this is a good application of time series modeling. Here's the problem. When we have a series like this, I have one repeated measure, let's call it y, through time. I observe, the values at particular points through time. But the problem is that each value is closely related to the one that came before it. So in general, you can see the data points are closest to the data point that came before it. Sometimes you see jumps. So we get a point from here to here. You see big jumps in some cases. But overall, we have data points that are like related to the one before that came before it. This violates independence. So what we're going to do is talk through, first off, how you can see this using a lagged residual plot, and then we're going to talk about some ways of handling on the edges some of these issues of autocorrelation. So this is just a picture. This is the original series I just showed you, but I've just squished it. This is a picture of the 2 values of y, one after the other. So the horizontal axis is yt negative 1. So this is for whatever point in whatever measure I have, I'm going to plot the one before it. So I have 2 points. I'm going to plot the one before it, and then so I'm plotting that on the horizontal axis, and then I'm plotting the point on the vertical axis. So I'm just plotting one point against the one that comes before it. Any questions about this figure? So one point against the one that comes before it. And what you can see is exactly what I mentioned on the previous slide, right? Like, this is a picture of autocorrelation. I have a measure and what I've measured in the previous period. And those values are correlated. The weather today, as nice as it is highly correlated with the weather that came before it. Some of this is just seasonal, but also like weather comes through and changes for short periods of time. So almost everything we see is correlated like this. This is a picture of autocorrelation. I have one value plotted against the one that came before it. If we build statistical models of this data, so this is the same data set, and what I'm doing here is building, we're going to call this model 1. This is our levels model. I haven't done anything to it. I'm just trying to predict y using time. What I have here is y as an outcome variable. I have an intercept term, I have a slope term, and I have time as the predictor variable. I would say this is a no-no. I'm going to show you, I'm started using baby terms now that I have a child. Actually, I've never said that to Max, so. I'm using time to predict the y value. And this is just a picture. It shows a positive trend. So as time goes on, I see that my outcome variable is going up. But the problem with doing it this way is we end up sort of carrying through the problem of autocorrelation into the error terms of our model. So what I've shown a picture here. The model, the data, and then the error terms in green. And what you can see is that we're systematically wrong in the same direction repeatedly. Because the underlying data is autocorrelated, the error terms are also going to be autocorrelated. Okay, so this is just a picture of the residual plot, which we talked about last time, and the lagged residual plot. So this first figure is just on the horizontal axis, I have time. So this is the predictor variable. And then this is the residual. So I'm just plotting these two together. I could have put the predicted value on the horizontal axis, which I think would be maybe more correct. But either way, we can see the relationship between the data and the error terms. The more important scatter plot for thinking about time series models is the lagged residual plot, where just like I showed with the autocorrelation figure, where I had y against y in the previous period, here I'm just showing you the residual plotted against the residual in the previous period. So I have every residual plotted against the residual that came before it. If this figure looks similar to the autocorrelation figure, it's because it is. We can see autocorrelation in the lagged residual plot. I'm making the same mistake in the same direction in periods back to back with my statistical model. This thing is making errors in the same direction repeatedly. And you can see that here. The errors are correlated with the error that came before. This is a problem. The reason this is a problem is because our, all of our assumptions that go into how we think about p-values depend on us selecting independently one value after the other. So this actually will give us incorrect p-values. Our level of confidence will be wrong if we build a statistical model that has autocorrelation. So we have to do something about this. If you leave it here, I think I would be dissatisfied with your time series model. You can use the time series model, but you just have to do a little bit of extra work. If you make a note of the autocorrelation, that's a really good first step. But we can do other things on top of this. All right. Y'all want to do some work? Let's keep it snappy. We'll see if we can get out before the end of the period. How about? So we're actually going to, I have a data set that we're going to verify Okun's law. Let me just, can I give you a, let's see, Okun's law. I'm not a macroeconomist, so don't treat me as an expert on Okun's law. But this is the Wikipedia page for it. It essentially tells us the relationship between, so we have quarterly change in the unemployment rate. So with unemployment some measure of unemployment on the horizontal axis and the change in GDP on the vertical axis. So it tells us like unemployment goes up when we have decreases in GDP. So when GDP goes down, unemployment goes up. Any questions here? We're going to verify this. I have data that will allow us to do this. All right, so first thing we'll do is hop over to the course page. If you click on Notebook, thank God it opens. I'm going to save a copy in Drive, and then we're going to talk about Okun's law. Okay, so the first thing I'm going to do is just run the imports and then load the data. So this is a data set I've called Okun, but we're going to look at the actual variables. The variables are taken from the Federal Reserve. We collect lots of good data. So here I have GDP. So this is just a measure of GDP. Here I have unemployment. I have quarter. So this, the year is broken up into 4 quarters. I have year. So this is the year that the observation was recorded. And then I have a time measure, but we're not going to use anything beyond these first main variables here, GDP and unemployment. Okay, so the first thing we're going to do is actually just set up a statistical model to predict GDP using unemployment. Right, so we have our Okun's law figure has GDP on the vertical axis and unemployment on the horizontal axis. First thing we're going to do is build that model. We're going to call it model 1, and then we're going to test its residuals. We're going to first check the residuals, and then we're going to lag the residuals and plot the lagged residual plot. Y'all want to do some work? I'll take that as a yes, even though it doesn't look like it. I see you. I want to be outside too. So we're going to take like 2 minutes here. The first thing to do is set up your statistical model. I've given you all the code except for this part. You want your statistical model to be called model 1. You write down your equation, and you go from there. I guess the slides aren't posted yet, so you don't have the slides to go off of. A little tough. You're going to be doing this in your projects, so treat this as a test of those skills. Meanwhile, I'm going to try to post the slides. We'll take 2 minutes here. It's 1:20, so we'll go to 1:22. Also, tell your neighbor they're good at code, even though this feels like a cold start. Tell them they're good at code.
Good at code. You know.
Oh, this is not for you.
I know, it's just. So this is an HTML.
The website?
Yeah. So if you're defining class multiple times, oh no, I've never used HTML. How does that work?
Defining class. Oh, here.
Multiple times,
Yeah, so it's like you can. It's like an object. So this is an image object, and then you can. I have class placeholder button is like a type of image, so it like looks a certain way. Class is like what clothes it's wearing. It's like the way it looks, and then this is just a certain type of way it looks. It's like that's the design. The class design is the... It looks really complicated. It's actually, like, once you see it and understand what's going on, it's not actually that complicated. All right. Someone want to tell me the code you wrote here for the first model? Everyone's avoiding my eyes. Yeah.
SMF, OLS, and then GDP.
GDP. And we can make sure we're spelling this correctly. So I want lowercase.
Yeah. And then squiggly. Unemployment.
Yeah. Okay.
And then comma, data. And then fit.
And then fit. Nice. Run this, and we get this little thing. I'm sorry. We're like most of the way through this semester. Remind me of your name.
Alex.
Alex. Yeah, thank you. That was very good. And then I'm just going to take model, print out the summary, and then just show the first table. You can show the full thing if you wish, but this is just the first table. If you wish, you can also show the scatter plot. So I could say SMS, scatter plot. And let's see, does Gemini get this? Nope. Data X is equal to unemployment, Gemini, GDP, and we'll get this thing. We can turn this into a reg plot. Let's turn this into a reg plot. Reg plot. And we get a line through it. Yeah.
Could you go back up to the OLS one? I know this is a really stupid question.
I'm sure it's not.
Wait, how do I get the squiggly thing on the?
Oh yeah, so
on the
that's
keyboard?
right under escape. And I think
okay.
I think you have to
Thank
use shift.
Yeah.
Yeah, see, you're not the only one with that question in the classroom. Here's the thing, if you ask questions, if you have a question and you ask it, almost certainly someone else in the room benefits because of it. Sometimes I bring candy for questions, but are you children? Well, I guess you don't have to be a child to like candy. Maybe I should bring candy to class. Okay, so someone tell me, does this look right? What do you think of this model? It doesn't have to be perfect to be fine, but the way we check whether this model satisfies the assumptions of the general linear model, we have to check the residuals. So what I'm going to do, I wrote you this code. I'm not feeling generous today. I wrote this little line here. If you defined your model as model 1, you can run this, and you're going to get both the residual plot and the lagged residual plot. So this first one is the residuals against the predicted values. So the horizontal axis, I have the predictions. The vertical axis, I have the residuals. And I don't like this at all. The second thing is I have the residuals against the lagged residuals. Does this look fine? The lag plot? I see some no's. Someone tell me why this is not fine. Are you all getting this on your computers? Why is this not fine? Pete?
It's like every single residual is determined by the one before it almost like a perfect diagonal.
It is so close to a perfect 45-degree line. This is a real problem. This tells us, like, almost everything is just simply determined by the period that came before it. Like the best predictor of anything, I mean, it's not time, it's just the previous period. Any questions here? Yeah, Zach.
Will it look like that if we shrink the scale?
Yeah, so I mean, think about what happens here. This is just a 45-degree line. Both scales are the same on both axes. So we're just like tightly clustered to the 45. It's the diagonal line. Yeah. No matter what scale we look at this. All right. This is the problem. If you show me this and this is where you end, I'm going to be a little unhappy with you. So I'm going to show you some ways of handling these problems. If you're going to do time series, you're going to have to handle these problems. And you're going to have to show me your autocorrelation plot. Okay, so let's talk about some alternatives here. Let's see, are the slides up? Okay, my formatting is wrong. Wow, this is a real drama. Maybe by the end of next exercise, we'll get this fixed. So here's this is the code if you had the slides, which maybe you do by now. We're going to talk about a second model. That's our simplest model. We're just predicting the outcome using the input variable. What we're going to do next is think about relationships that we've taken first differences of. So remember what the problem was in the previous example. Almost all of the predictive power of almost all of the relationship in the data was coming from, like, the best predictor was the period that came before. So what we're going to do is remove the period that came before from the data. This is what we call a first difference. So instead of using yt as our outcome variable, we're going to use yt minus yt in the previous period. So yt minus 1. So I'm just going to take yt and subtract off y in the previous period. We're going to call this delta y, or just difference y. We can do this really easily in code, as we'll do in a second. This is a picture of yt, so this is our original data. And you can see there are there's strong autocorrelation here. The errors are all in the same direction, or they're in the same direction repeatedly. But when we look at the differenced model, because I've taken out the period that came before, I've just subtracted off the value from yesterday, all I'm left with is a change. So I'm just asking whether it's gone up or gone down, instead of asking where is it. And because of this, I have much less of the original autocorrelation issue. So to show this, well, first let me ask this question. What would the first differences look like if there was a positive trend? Here, there's no positive trend, no trend at all, actually. We've centered the changes on 0. So there's no relationship with the data through time. The only trend we see are these local ones, because things are just correlated with each other. What if there was a trend? Well, for the sake of getting you out of class early, I'm going to answer my own question. Here's original data, so yt, and this does have a trend. It looks like the yt, whether this is like GDP or whatever measure we're measuring, is increasing through time. It's going up. Think about what would happen if we took a first differences and plotted that delta y on this axis. Like, spend maybe 10 seconds thinking about how it might go. You're taking one data point and subtracting off the one that came before it. They're all increasing. Do y'all know what this would look like? It's going to look like this. Each one, I mean, there's some variation here, but I'm subtracting off the value that came before it, on average, because it's increasing, the one that came before it is slightly lower on average. So the average of the differences will be positive. So if we're looking at first differences, we can test for trends by using an intercept. All right. This is my line. This picture shows us that there's a positive relationship. And I also don't have autocorrelation, or not as bad of a problem. Okay, so nice. Vertical intercept is positive, which means there's a positive relationship, a positive trend in YT. And then the slope coefficient is 0. It's just increasing at the same rate through time, almost like the second derivative. All right, and then I'm just going to go ahead and plot these things. This is the residual plot. I don't see problems. Of nonlinearity or heteroscedasticity here. And then this is the autocorrelation figure with the lagged residual plot. And I also don't see strong issues of autocorrelation. Any questions here? So we're going to do this same first differencing approach for Oken's law. The first thing we're going to do is actually just take a first difference. Python, we do this so often that Python actually has a built-in feature called diff. And we're going to do a first difference, and then we're just going to plot this. So if you hop over to the exercise, I've given you no code, and it's your job to look at the first differences. We'll take maybe 2 minutes here. It's 1:34. We'll go to 1:36. Try to set up the model. If you want to plot this out, predict the change in GDP using unemployment. So maybe I should write this out. Predict change in GDP using unemployment. All right, someone want to tell me how to write this code? Andrew.
Would just be the first one, like the same as the first one's SMF/OLS, and then instead of GDP, it'd be
GDP diff,
and then
squiggly.
this will be unemployment data
Run this. Okay. And then if you wanted to, we can plot the relationship. We can run the model, but sometimes I think, all of parts 1 and 2 were devoted to visualizing our data for a good reason, right? Like, we need to understand what's actually going on behind the scenes so we don't make mistakes. So here we have, let's just copy this one. We have reg plot. our y value now is going to be GDP diff. We run this. Maybe this looks a little better. Anyone think this looks better? The last one was like wildly wrong. This one is, I think, a lot better. But let's check the residuals. So here I'm going to run model 2 residuals. What do y'all think? Does this look like linearity and heteroscedasticity or homoscedasticity? I think this looks pretty good. What do y'all think about this one? Is this, do you think this has autocorrelation? See, conflicting answers right here. I love that. I think you could make a case that this is either way. I think there's a little bit of autocorrelation here, but it's definitely much better than the previous one. This one we saw a very strong relationship. This is way, way better than that. But we can do better. This is, so this is actually not Oken's law. This is the figure we just generated. Oken's law tells us something slightly different. Instead of the relationship between unemployment and the change in GDP, it tells us something about the change in unemployment against the change in GDP. So what we're going to do next is build a double difference model. Okay. So here we're going to have two differenced variables that move together. So instead of, in the slides, instead of predicting y with t, I'm going to predict it with a change variable, delta x. So this is just a picture. The horizontal axis, I have the change in some time variable. So we have, we're indexing this by t, and then we're just going to compare that change variable to the change variable on the vertical axis. This is more of the environment that Oken's law lives in. It's not using just the raw variables themselves, it's using the changes. What this does is we removed some of the autocorrelation from the outcome variable, our GDP, by first differencing. We pulled out the value that came before. But unemployment suffers from the same problem. So what we're going to do is pull out the relationship, the sort of dependency between time periods by first differencing both the predictor and the outcome variable. Beta 0 is going to capture, so the vertical axis is going to capture the change in y, and beta 1 will capture the short-term relationship between the variables. Okay, I guess this is only true for using time as a predictor. Okay, but the interpretation here is, how do changes in x relate to changes in y? That's what beta 1 is going to tell us. So let's hop back over to the slides. Are these called slides? I don't think so. Insert self-deprecating joke. Thank you, appreciate the laughter. So then what we're going to do is create a first difference in unemployment. I've given you the code for this because I'm feeling generous. Then we have our two difference variables. So my outcome variable is GDP difference like before, but now I'm going to unemployment difference as the predictor variable. If I run this, I get this model. And let's just check what this looks like. So I'm just going to I'm going to create unemployment diff. What do you all think of this? I think this is fine. I'm not quite sure about the strength of the relationship. It's definitely downward sloping. But to check whether this slope is statistically different from 0, we have to go back up and check the regression output. So here I have an intercept. it hits 0, so it hits 0 right around 65. And it hits, and the relationship between GDP and unemployment is negative roughly 80. We have a p-value that's very, very small. So this tells me that it's not very compatible with the null hypothesis of no relationship. So this is very incompatible with a null, our default null. What this tells me is every 1 unit increase in unemployment, I see a decrease in GDP of 80. So every time unemployment goes up, the change in GDP goes down. So we see a negative relationship. The last thing we're going to do is predict the residuals, or plot the residuals. When I plot these, the residual plot looks pretty good to me. I think there might be more issue of heteroscedasticity. We have more variability around most of the data. Like this doesn't look very variable. Autocorrelation looks about the same, maybe slightly better than in the previous model. But either way, at this point, we're in the ballpark of being fine. There are still other issues. If you were to like write a paper and try to get it published somewhere, you'd have to handle like many other kinds of things. But this, at least at a surface level, puts us in the ballpark of being reasonably fine. Okay. Y'all want to do one more thing? And then we're actually going to plot Oken's law. We're still not quite at Oken's law. For the sake of time, I'm just gonna cruise through. I think we're gonna get out ahead of schedule. You happy about this? Okay, so here, in the model we just ran, beta 1 now represents the short-term relationship between changes. Because we're dealing with changes, like differences, the interpretation of beta actually becomes more challenging. We're going to spend a second talking about this near the end. The last thing we're going to do is think about growth rates. Y'all remember like elasticities from your intro economics classes? Like percent change in something, where you have percent change and then you divide it by percent change in the other thing. What we're going to do is think about percentage changes. Python handles this very nicely. So we're going to talk about growth rates. So this is, you have the change on the top and then you have the change on the bottom. This may feel like extra to be doing this, but I'm going to show you the reason why we do it. This is so we have delta yt, and then we just divide it by either the current period or the previous period. I have the previous period listed in the slides. You could also use like the midpoint method if you're into that, which is the more correct way of doing this. But either way you do it, it's going to be roughly the same. So here's, I have a data set here. This is just a y value. And like GDP, I have an exponential relationship. GDP is one of those things where it grows, but it compounds. Like your money in the savings account grows by compounding. So it every year it grows by a percentage. So if we just look at first differences in these kind of exponential relationships, it looks like this. So at the beginning, the change isn't very large, simply because it's not very big. So any movement isn't going to be very large. But then as it starts growing, the changes appear larger. They are larger. So you can see that the changes grow through time. And if we were to run a model on this data, this would present other kinds of issues. Like the changes for small values are not very meaningful, while the changes for later values are very large. But we can account for this using percentage change. And all we have to do is divide by the base rate, or the the previous period. So here I've used percent changes instead of just absolute changes. And this looks much, much better. Oken's law is written in these terms for these reasons. GDP is just a measure that we have to think about percent changes because it scales much like this figure. So we're going to use percent changes and plot that relationship. Any questions here? So here's a picture. So I've used growth rates on both sides, and I think this looks just much, much nicer. Okay. Anything that grows exponentially is a good candidate for this. All right, so we're going to hop back to the exercise. So here I have two things. I have the growth rate of unemployment and the growth rate of GDP, and then I'm just going to fit that model. To be technically correct, we have to use the change in the unemployment rate, not the percent change, and then the change in GDP growth. So it's percent change in GDP. This figure isn't labeled correctly, but then we also have just change in unemployment rate on the horizontal axis. What we have written here is the growth rate on both sides. So we're going to run this, and then we're going to run Oken's law in the last step. Okay, so nice. Here's the model. This tells us that there's a positive intercept. There's a negative relationship between the two variables. Both of these coefficients are very incompatible with 0, which is nice. It tells us that there's something going on here. And then we're going to run the residuals. This lag plot is the best one we've seen so far. I think this is about as good as you're ever going to see. So we've dealt with a lot of the core problems of autocorrelation. We've gone from a world where we have strong autocorrelation. Look at this. Remember this? We've transformed this data into something that looks much, much better. So if you're dealing with time series models, this is the way to go. There's a whole lot more to do, but this is the core of it. The last thing we're going to do is actually just plot directly Oken's law after I pause and ask you for questions. Any questions? Let's plot Oken's law. Oken's law tells us we want to predict the percent change in GDP on the vertical axis against the difference, the change in unemployment on the horizontal axis. So nothing we've done so far is the exact replica of Oken's law. What I want to do is plot on the vertical axis, I want y is equal to, what are we calling this? GDP growth. GDP growth. And then x, I want this to be unemployment difference. And then I'm going to use data is equal to data. If I plot this, do you all think there's a relationship here? I do too. So let's run a statistical model. We're going to let's run GDP growth and then unemployment diff and plot this. And then let's change this to reg plot. So what I see is that every time, every 1 unit increase in the unemployment rate GDP will grow at a 0.0128 percentage points slower. So growth rate slows down when unemployment is higher. It doesn't tell us what the growth rate is, but it tells us that it will go down. Okay, so this is Okun's law. This is a demonstration of some of the issues we can run into when working with data, and a very good application of the lagged residual plot. This is why we care about those things we talked about last class. And if you're working with time series data, this is the full tool set I need from you. Any questions here before we take off? I don't think I've ever let class out 20 minutes early. So this is the first. Yeah, question.
Sorry, for the exercise, which one do you want us to do? Like, which one do you want us to do?
I think there are there 2 entries? So I think, so you can put in either one. I'm sorry, you can put in, oh, you're asking which model.
Yeah.
Just pick one and put it in. Maybe pick the first one. If you leave now, it's 22 minutes early? What are you going to do with all your time? Stick around. I'll be around in this room until everyone leaves for questions about your projects. We're going to start talking about this in more concrete detail next class, and then we'll do some review. I've given everyone an extension through Sundays on the homework, so take your time. Yeah. I haven't posted them on Gradescope yet.
Okay, I don't
Yeah.
see one.
They're on the course page, but not on Gradescope.
For the these two, are we? Which ones are?